like I promised, I'm going to finally prove that the limit of the nth root of n is equal to 1, where n is some positive integer. I've used this fact many times in previous videos, but haven't proven it. But let's now just suppose that the only tool we have is the epsilon capital N language. And in the future, I will show different ways. But here, let's just use the epsilon language. So we want to prove for any epsilon, right, for any positive number, we want to find out if there exists such a capital N. Can we find such a capital N so that when little n is larger than this capital N, can we show that the absolute value of my desired sequence minus my desired limit, can we show that their absolute value is less than epsilon? In other words, can we show that when little n is large enough, the distance between the sequence and 1 can be small enough? Remember, the absolute value means the distance between 2 points, right? So in other words, this and 1, sequence and the 1 can be close enough. So again, we're not going to solve for the inequality just straight away. Again, we're going to use the common technique many times like I used before. We're going to loosen the inequality appropriately. So first of all, we know that the nth root of n, as long as n is some positive integer, it is always going to be larger than or equal to 1. That's easily verifiable. Therefore, I don't need the absolute value in this case. So therefore, the absolute value of nth root of n minus 1 is easily just equal to itself. The nth root of n minus 1. Can we loosen it just a little bit? Well, first of all, I'm going to use the AMGM inequality. Remember, as long as we have n positive numbers like A1, AN are all positive, then we can have the AMGM inequality. That is the nth root of A1 times all the way up to AN, nth root is no larger than the arithmetic mean. That's divided by n, A1, plus all the way up to AN. In this case, what's my A1? What's my AN? In this case, I can rewrite the nth root of n into the nth root of just 1 times 1 times all the way up to 1 times square root of n times square root of n. So I've rewritten n into a product of series of positive numbers. So how many ones do I have here? I have exactly n minus 2 ones here, right? So including the square root of n and square root of n, how many positive numbers do I have? I have exactly n positive numbers inside the nth root. So according to the AMGM inequality, right, I can have the following conclusion. That is, the nth root of n is no larger than first of all, I have n on the bottom, and I have the sum of those positive numbers, right? So I have 1 plus 1 plus all the way up to 1, and plus square root of n plus square root of n. Like I said, how many ones do I have? I have exactly n minus 2 ones in here. So that is equal to divide by n. So n minus 2 plus twice of square root of n. All right, so therefore I can loosen my inequality. So that is no larger than, just copy it down, n, then n minus 2 plus twice of square root of n, I have to minus 1 following that. Then I can just use the common denominator, just n, then therefore I have to minus n on the top. Then I can just say that is actually equal to n cancel out. I have n on the bottom, and I still have twice of the square root of n minus 2 on the top. Then I have to further loosen it. It's less than or equal to, here I just minus some positive number, but down here I do not minus this positive number, so I've now become larger, right? So I only have twice of square root of n. Now I can just say that is equal to 2 over square root of n, right? So for the first step, the absolute value is equal to this expression, and that is no larger than this. Then I can let this be less than epsilon, right? So I want to prove that this absolute value is less than epsilon. So I've loosened the inequality and really finally reached the epsilon. Now I just have to solve for this inequality. So I can divide square root of n over to that side, divide epsilon over to here, and square both sides. So in the end, I have little n is larger than 4 over epsilon squared. Now, so in other words, as long as n is larger than this value, then this inequality is true, because this expression is shown to be no larger than this expression, and that is less than epsilon. Therefore, as long as little n is larger than this quantity, then my absolute value of this expression can really be smaller than my given epsilon, right? So any arbitrarily chosen given epsilon, fix it, then that's less than epsilon, right? So what is my capital N? My capital N is the floor of 4 over epsilon squared, right? I can use these quantities because this may not be some positive integer, maybe some decimal, then I have to use the floor. So that is my capital N. Now, what's the motivation of me writing n into 1 times 1 times 1 times square root of n times square root of n? So the motivation is that as soon as we see the nth root of something, that motivates us to use the AM-GM inequality. That is a very common technique in analysis. And then, how on earth did we write it into 1 times square root of n times square root of n instead of writing it into 1 times 1 times 1 times just n, right? How many ones in here? N minus 1 ones in here. Why not rewrite it like this? I'll leave the question to you. Yeah, let me know in the comment. Why not write it like this? Just give it a try and use the same technique. And in the end, you will realize that the reason we don't write it like this. And next question is that, can we rewrite n into 1 times 1 times 1 all the way up to 1 times the cubic root of n times cubic root of n times cubic root of n, how many ones? N minus 3 ones in here. Can we rewrite n into this and use the AM-GM inequality and finally reach the same result? Also, my question for you is that, can we rewrite n into 1 times 1 times 1 times 1 times the kth root of n times all the way up to the kth root of n, where we have how many of kth root of n? We have k of them. How many ones do we have in here? We have n minus k. Many ones in here, where k is some fixed positive integer. Let me know that in the comment.